coming in. Thank you very much, everybody, for showing up and joining us today. It is Kontur's distinct pleasure to present Ken Mazer of Infrasense, Dr. Ken Mazer from Infrasense, as he reviews his latest and greatest advances in 3D GPR concrete pavement evaluations. Today, I'm Kent Martin, Global Marketing Director for Kontur, and Ken doesn't need any further introduction than that. Everybody is aware of all the incredible work he's been doing over many years. And just as a quick introduction into the webinar itself, we're going to have all the participants muted. And if you could just use the Q&A function to ask any questions. We'll probably save most of the questions towards the end. We can just do a quick Q&A after that. And if there's something that does pop up in the meantime, I'll kind of monitor that. And if it's germane to where we are in the conversation, I'll break in with Ken. You should be able to see all the questions and answers there. So without further ado, let me stop sharing here and turn the podium over to Dr. Ken Mazer. Thank you.
Okay, thank you, Kent. Let me just share my screen. This would be this screen here. So are you seeing my screen?
Not yet.
Oh, I gotta say share. Okay.
There we go. You're coming up now.
All right, thank you. Well, good afternoon, everyone. Thank you for the intro, Kent. And thank you, everybody, for joining. I'm Ken Mazer. I'm with Infrasense. My background is in non-destructive testing of highway structures, pavements, bridge decks, and other types of facilities. And I've had a major emphasis on work with ground penetrating radar. And over the past, I think, 15 years, I've had the opportunity to work with 3D radar and have had some interesting applications, some of them with concrete pavement, and that's some of those experiences I want to share with you today. So what I want to talk about in my presentation is first go over the different types of concrete pavements that we've encountered, some of the conditions that we detect, what's particularly unique about 3D radar for these applications, discuss some of the analysis methods and tools that we use, and then the bulk of my presentation will be on some case studies. So the kinds of concrete pavement we look at are jointed concrete pavement with dowels, jointed concrete pavement with continuous reinforcing and dowels, just straight continuously reinforced concrete pavement, and then composite pavement, which is any of those other kinds of pavements covered with asphalt. And the types of conditions that we're looking at are one with dowels and tie bars, simply identifying where they're missing or where they may be misplaced. On the lower left-hand picture, changes in pavement construction, particularly laterally along the road, if the road has been widened or extended, where does that boundary exist? It's not an easy application with a conventional radar, but it's very straightforward with 3D radar. Pavement thickness, which is an application that's been ongoing for a long time, and then identification of voids or excessive moisture underneath the surface. So 3D radar, why do we use it? Well, it provides complete coverage across the width of this array. So you can see here the array has this particular antenna there at 10 or 11 transmitters and receivers, and the combination of transmitters and receivers gives us 20 different channels of data. And those 20 channels of data spaced 3 inches apart give us complete lateral coverage as well as continuous longitudinal coverage. This is a picture down below of a ground coupled equipment setup with the antenna laid out across the surface with this particular pattern. So as I said, with this setup, we can detect features that vary laterally as well as longitudinally, such as dowels and void areas and rebar and things of that sort that cannot normally be picked up with a single or dual channel data. Of course, the consequence of this array is that we have much more data. In this case, 20 channels of data versus what we traditionally might have 1 or 2 channels of GPR data. But fortunately, we have developed, and we're working with some more efficient ways to analyze this data so that they're tailored to meet specific needs and they're not particularly burdensome. So let me mention a little bit about some of these analysis tools. First, we have Examiner software, which is developed and provided by Kontur, which gives us a spatial display of the data, makes it easy to annotate locations of interest, and allows us to export the data for further analysis using kind of application-specific software. We've developed a means for automating the detection of dowels and tie bars, locating them, depth, their spacing, etc. And I'll talk about that as one of the applications. We've also implemented what's called a reflection and activity analysis that enables the detection of stripping in asphalt pavement and voids under concrete pavement. And we still have the ability to do conventional single channel data if we want to do pavement thickness and we're only interested in getting the thickness along the particular wheel path. We can always analyze a single channel. So the conventional single dual channel options are always there. So let me talk about the first application, which is automating the detection of missing or misplaced dowels and tie bars. On the left here are some of the defects that have been documented with dowels and tie bars similarly. They're either misplaced laterally or longitudinally. They're sometimes at an angle. This is in plan view, and in vertical view, there can be at the wrong elevation or at an angle in the vertical. The problem is with misplaced dowel bars, for example, they can result in joint locking, spalling, and cracking, and ultimate failure of the pavement, such as shown over here. So these are conditions that the agency wants to know about before the problems actually show up. With 3D GPR, dowels and tie bars show up very clearly. The upper picture here is what they call a depth slice. So basically it's a plan view of a concrete pavement at the depth of where the dowels and ties are located. The longitudinal joint is somewhere below this little blue line. The vertical lines here are the tie bars, and the so you see these tie bars are about 2.5 feet apart, and the dashes, the blurry dashes here, are the dowel bars, and they're spaced longitudinally at the joint spacing, which looks like about 15 feet. And laterally, they're spaced about 1 foot apart, except there's a gap at the longitudinal joint where there should be. So they're very readily detectable, and what we're interested in are things like I'm showing on the bottom, which is the area where they're totally gone. And this is a section of Highway 23 in Wisconsin where this particular issue turned up in one of the construction projects. So the data is clear, the issue is clear, but rather than have to pour over all this data, miles of it in some cases, we've been able to automate the detection of the dowels and tie bars. And by automating the detection, we can also identify where they're missing or misplaced. And that's shown in the next slide. So the software basically identifies, detects, and maps out the location of these, in this case, the dowel bars. So on the above is the Google Earth image with all of the detected dowels shown in yellow dots. Each dowel has an ID. It has a location in terms of distance and offset. It has a lat and long. It has a depth. It has a lateral spacing. It has a longitudinal translation, vertical depth, as well as angles in the horizontal and vertical direction. And below, these locations have been mapped in a depth slice view, like I showed you in the previous slide. So you can actually see where the detected dowels line up with the image dowels. So they line up pretty well. So what this software does gives us the ability to get statistics for each for a pavement section. So you can see, for example, this would be the depth of the dowels, what the distribution of the dowel depths are. So we can see, okay, we've got some outliers here at this end and the other end. So we can see the stats. The data is available also in spreadsheet format, and we can make queries. For example, we can tell the program, show us locations where the tie bar spacing is greater than 10 feet. And it'll point us to a location like I showed in the earlier slide. Show locations where dowel spacing is greater than 2 feet, and it will identify and map out those locations. Or show us places, if the dowel placement depth is supposed to be 5 inches, we can have the program show us where the locations are outliers, like greater than 7 inches or less than 3 inches. And all these queries are presented in the Google Earth, as I showed before, as well as an examiner, so you can see the images and in spreadsheet format. So this capability is just recently kind of developed and is currently being evaluated by the National Road Research Association, which sponsored it, and should be more available in the near future. The next example I'd like to go over is a specific case study of a project in Massachusetts. The goal here, this was Highway 133, Andover Street in Lowell, Mass, 1.37 mile section. It was built, you can see carefully, this is a picture of the original construction in 1929. That's really the only records that were available for this. But the agency had absolutely no idea what the construction consisted of. So the goal here was to try to identify the subsurface conditions so that they could optimize the funding available for restoring the road and putting it back into good condition. It was surveyed with a vehicle-based ground-coupled 3D GPR system. It took one night, which was really not even one night. It's basically it was 3 lanes plus 2 shoulders. We generally do 3 passes per lane, and so it might be like 13 round trips, which at the speed of typically a ground coupled system runs about 20 miles an hour, would take about 2 hours. So not very much time. And the goal, of the analysis was to report the pavement construction and the limits of the different constructions, show the concrete thickness, show missing and misaligned dowel and tie bars, and areas of potential voiding, and use the results for pavement rehab. So I'm going to show you the examples of some of the results. Okay. So this is is a depth slice, so shown kind of overlaid on a Google Earth image of the road. So you can see the road has an eastbound lane, a westbound lane, turning lane, a westbound and right shoulder, and an eastbound shoulder. This is a depth slice, like I showed earlier, at the depth of the rebar. And this kind of looks like the original construction. It's sort of jointed, reinforced concrete pavement. Reinforcing seems to be spaced at about 1.5 feet, but a very clear image of how this thing was built. We look at the next image. Further down the road, very different construction. What appears, and we're doing a little bit of archaeology here, is that the center, the driving lanes, most of them were rehabilitated and replaced with more densely reinforced concrete pavement. And then if we look a little further down the road, we see another section appears to be replaced by a jointed plain concrete pavement. You can see the dowels here are these little dashes, and the joints are where the dowels are repeated, and they're not that regularly spaced. So kind of a clear picture of the things that have happened and different constructions that exist on this road. So these conditions were laid out spatially in Google Earth. So we have different colors for the jointed reinforced concrete, for the jointed reinforced concrete with no dowels, and for the jointed plain concrete pavement. So the overall image is shown here with the different colors, and this is just taking a blow up where the Andover Street label is, and you can see the detail where the shoulder areas had the initial construction, and the center line had both the jointed reinforced concrete with and without dowels. Also, we could see areas where there are specific defects with the tie bars and where they're missing and misaligned. So the blue line is where the tie bars are present, which is a lot. Well, the yellow and blue lines are the longitudinal joints, and then the yellow lines are where there are tie bars, where they should be connected to joints. The blue lines are where there are no tie bars, and there, if you look carefully, you can see some magenta lines where the tie bars were misaligned. Also of interest was the thickness, which varies quite a bit across the width of the pavement, depending on the types of construction. So closer to 9 and 10 inches in the center line, in this particular image, closer to 9 and 10 inches in the center areas, thinner on the outside areas. The little blue dots just represent the thickness values at these intervals. And so that information is available for the complete length of the project. Also investigated was the presence of voids. Voids underneath the concrete pavement usually result in high reflection activity, which is represented by these bright spots. So these are identified as areas of potential voids, and they can also be mapped in Google Earth so that they can be viewed in terms of the overall layout of the project and rehabilitation planning. So given the limited amount of data that the agency had at the origin of this project, the information provided here enabled the agency and the city to, they didn't know about these 3 distinct constructions. So it enabled them to implement a rehabilitation plan that was responsive to these different types of constructions and enable them to prioritize the different types of constructions and rehabilitations accordingly. Also provide information to the contractor so that they have a better idea of the existing conditions and there are less likelihood of surprises during the construction process. So my next application example, go here, is in Georgia. This was I-85, and the goal here was to map the continuous reinforced concrete in the pavement. This was a 27+ mile length of highway. It was surveyed with an air launch system, driving at continuous normal driving speeds. And I think given the number of lanes and the number of passes per lane, this was a 3-night project. The results were geospatial and tabular reporting of rebar depth, areas of different types of construction, plain concrete versus reinforced concrete pavement. And the results were used to identify areas where there was shallow steel. Concern about shallow steel was whether or not grinding could be performed at this time and how many additional grinding cycles would be feasible before an overlay would be needed. So the data on this project looks something like this. This is now what they call a B-scan, or a vertical cross-section through the pavement. And the little white ripply line here is the rebar. And it's shown at about it's about a 3, this is time, not depth, but it turned out to be about 4 inches, 4.5 inches deep. But it shows up very clearly in the data and can be easily tracked with automated tracking tools that are available in Examiner. You can also look at the rebar with a depth slice as shown here, similar to what we looked at before, and you can see the bars are the vertical lines going across the pavement. And then the rebar depth can be mapped, shown here. So the color coding, and this is laid out on Google Earth. So the color coding provides an indication of the depth of the rebar. You can see it ranged from as low as below 3 to close to about 5+ inches. So it gave the agency a very clear picture of what sort of rebar depth and variation they had. Also could determine all the statistics, the averages, the max of the min. So basically they could avoid grinding if it was too thin, and know exactly where those areas might be. Okay. So final case study is in South Carolina, and this was another dowel and tie bar application. There was some joint distress that was being observed and suspected to be due to alignment issues with dowel and tie bars. So the goal here was to investigate the layout, the dowels and tie bars, locate bars that are missing, shallow, or misaligned. This is a 2-mile section of I-26 near Charleston, and it was surveyed using vehicle-based ground-coupled GPR. Took 1 night to survey. Examiner software was used to analyze the data using the kind of depth slices that I showed earlier, and the results were presented geospatially and tabularly to show the dowel and tie bar layout. And the results were used to identify areas where it was appropriate to replace the particular slabs. So this is a kind of a depth slice similar to the ones that I showed earlier. What's different here is that these are multiple slices. Well, the other one showed that too. So this is a full lane plus, because we've got the tie bars at the longitudinal joint. So this is about a 16-foot wide depth slice. You can see all the dowels lined up nice and clear. You can see the tie bars at the edge. A very clear picture. The spacing of the dowel bars, 12 inches, as they should be. So this is a clear picture of what the pavement should be But then there are situations where things are what they shouldn't be. In this case, there was a spall at one particular location, and looking at that location, we can see that the dowels are totally misaligned. They're at an angle, and they're not lined up with the joint. We can quantify that. You can see the angle, and you can actually, this is the angle in the horizontal, but you can look in the cross section and see that there was an angle with the vertical as well. So all these things can be quantified. In addition, we were able to find that certain entire sections of certain lanes where dowels were totally missing. So in lane 1 here, we can see we have the dowels. In lane 2, we see the dowels are missing. So these conditions can be identified. They were mapped and laid out in Google Earth. So locations of missing dowels are in red. Present dowels are in green. Shallow dowels are in gray, dark gray rather. Misaligned dowels are in light gray on the left. And similar issues with tie bars. Missing tie bars are yellow. Shallow tie bars are blue. Misaligned are in light blue. So that kind of information was provided to the agency, and it was what they needed in order to specify the locations for slab replacement. So that kind of covers the examples I have. So let me just summarize, if I may. I guess the main message that I would like to emphasize is that 3D GPR reveals subsurface features and details in concrete pavement that are not otherwise known. You're really looking into the pavement almost like an X-ray and seeing things that you probably didn't know were there. And knowing they're there is very useful. The field measurements are fairly quick and minimized. The traffic interference is minimal. It does generate a lot of data, but the analysis tools are available to handle the quantity of data. And the results provide valuable information to highway agencies for diagnosing pavement failures, for determining appropriate and cost-effective remediation for those failures, and also for designing rehabilitation plans that are based on the actual pavement condition and not just what the assumed conditions are. And of course, it also prevents surprises during construction because conditions can be identified in advance. So that's what I've got. Thanks very much for sitting in. Be happy to answer any questions.
Thank you, Ken. And apologies about the mic echo. That seems to be on my side, so I'm going to keep muting myself. Any questions from the audience? Please type it into the Q&A. We have some clapping. That's a good sign.
Oh, I didn't know they had such a tab.
All right. Well, thank you very much. We have a part of our website under our customer projects that has a summary and a landing page going through with a PDF that you can download with this presentation in it, and we'll put the slide deck on there also. And we will get a recording out to all of our registrants within the next day or two. So can you show an example result for the void signal? There is a question for you, Ken.
So I had the example that I had. Am I still sharing?
Yeah, you're sharing.
Going back here. So this is a depth slice at the bottom, taken at the bottom of the concrete. and it's showing these high amplitude zones. Is that what the question is?
Yeah, Larry, he said thanks, so I guess that answered the question. Thanks,
Good.
Larry, for the question.
Okay. Thank you.
And have you compared the dowel and tie bar results to MIT scan? That is from Rico.
Yes. Now that question has come up. We haven't had the opportunity to have apples and apples comparisons to that. I know the question has been raised. I mean, to be honest, the MIT scan is a much more locally intensive scanning process. So I mean, it has its pluses and minuses, but uh, it's not, and it's based on, I think, the magnetic properties as opposed to the electromagnetic properties. But no, we haven't really done a direct comparison.
Excellent. Next question. How do you validate the accuracy of automated 3D GPR detection of dowel bars and reinforcement? Do you rely on coring, construction records, or other ground truth methods? And what accuracy have you achieved?
Usually the accuracy with reinforcing is based on cores. In certain projects, they will take cores and we will correlate, we'll do, regression of our calculated thickness versus the core thickness. And typically the results line up pretty well, maybe within a quarter of an inch.
Excellent. And have you explored the use of Orbit software from Ollie?
No.
Easy answer. And by the way, we can do something about that, Ken.
Yeah, you have to clue me in. I'm not aware of it.
We can do that. From Garrett, what kind of gain adjustments, if any, would you recommend to identify unbound layer interfaces, searching for voids around drainage features?
The question started with gain.
Yeah, what kind of gain adjustments?
I mean, usually the gain adjustments are for visual. And I think you just have to experiment with what shows up best in your situation. Depends on how deep things are. A lot of people like to use the variable depth gain. I tend to not like it because we're using pavements and we're closer to the surface. But yeah, it's really kind of application dependent, and you really have to just do whatever you need to do to make things stand out. If you're looking for isolated, that's gain, but there's also processing adjustments, which can highlight localized features. So, background removal with a short distance window tends to highlight local features. So you might consider that as well.
Excellent. Can 3D GPR data assess joint condition like LTE?
We can see defects under the joint, such as voids or excessive moisture, but having a void or having moisture doesn't necessarily mean the joint has failed or is moving. It just is a kind of a causal condition. What we have done is correlated LTE values with the detections of voids and found that at least in some areas where the load transfer was low, there was a void there. So it's kind of a cause and an effect. When your loss of support kind of causes the joint to start moving, and then once it starts moving, it kind of washes out. More stuff starts migrating out from below the joint. So but it's kind of complementary, but it's not an equivalent to flow transfer efficiency.
Excellent. And this next question is interesting. So particularly if I remember correctly, there was 2 types of antennas that you used. So the question is, does the testing vehicle travel on highway speed? From Rico.
So we use both kinds of antennas, ground coupled and air launched. Ground coupled is sliding very closely to the ground, so we're limited in speed to about 20 miles an hour. So well, depending on the location, the type of, there has to be some sort of traffic control, except maybe more locally on local streets. That's kind of the normal speed anyway. But on interstate highways, we usually have a moving closure, just traveling along. And with the air launch system, we require no traffic control. Is that the
And
question? Yeah.
that was the question. And
Okay.
for the air launch, what were you doing, like highway speed roughly?
Yeah. There's no, I mean, the only issue with highway speed is you can only get so many scans per foot. So it depends on the application. I think with the dowels and tie bars where you want that level of detail, you don't really want to go highway speed. And whereas pavement thickness, or even the rebar depth, rebars are sort of continuous, so you don't have to see every rebar. So you don't have to get so for some applications, speed is not an issue. It's application specific. You're looking for details at joints, you want to go slower and get more scans per foot.
Excellent. And a question from Larry was, on the antenna that you used, was it the 1820 Mark 6 or the Mark 4? And I think you have the Mark 4, right?
We have the 4, yeah.
Yeah. And his next part of his question is, what are the typical depth ranges you have found for the 2 different types of antenna?
It's hard to tell. It's very site dependent, but with asphalt, you can go down, maybe 30 inches. As we usually see stuff down to about 30 inches. And sometimes you don't know how far you're seeing because nothing's changing. So,
and that depends on which of the antennas you're using too, correct?
I think so, although I haven't paid a lot of attention to that. As long as it's,
as long as it works.
I'm looking mostly at pavements, and the pavement construction doesn't go down that deep. I mean, we've used the ground coupled for utilities and things, and that goes down maybe 5 or 6 feet. So yeah, I guess the ground couple goes deeper. Obviously, it's all the energy is going into the ground, and it has applications to utilities and things that the air launch probably wouldn't. So.
Excellent. And Larry, we can go into that further offline. Do you have other examples of void signal?
Not handy for this presentation, no.
Easy answer. What type of antenna was used for the concrete inspection?
Well, which one?
Actually, I think all had concrete in there, correct?
Yeah.
Yeah, so it was, the answer then is 2 types of antennas.
Both, yeah.
What trace interval spacing are you typically using for your ground coupled surveys? I guess the distance in between pulses.
Yeah, so that's application specific, but the application that is most demanding is dowel and tie bars. And there, I think we were using a scan spacing of less than an inch.
Excellent.
Yeah. For layer thickness and other things can be a half a foot, doesn't have to be that close.
And can the same 3D GPR data set be used not only for dowel and reinforcement mapping, but also for detecting moisture variations or base layer deterioration? And what are the current limitations?
So the same information can be used to detect moisture variations by looking at the amplitude of the signal from the bottom of the pavement. Generally, if the base is wet, the amplitude is high. That's sort of one way of doing that sort of detection. I don't know, but deterioration is a fuzzy term, so I'm not sure what. Can you be more specific?
And Hamid, if you want to add in another question after that one to verify your end part about the base layer deterioration. And then next question is, what is the resolution and spacing between the swept scans at 20 miles an hour versus 5 miles an hour for the ground coupled?
At 20 miles an hour, I think we can go like at 10. I'm trying to convert center, like a little less than an inch apart. I'm converting metric and English. 5 miles an hour, you have to fool the system because the system has a 10 centimeter limit. The collection system, it's a spacing limit. So,
well, it'll do less than that. But we do have that calculator that will show you the speed you can go depending on what your settings are, because we have 3 settings. Yeah. One is the distance in between scans, and then you have the time window and the duration. So, Larry, I can send you over that calculator, and we can kind of go through that. Grounder air, I'm not sure I understand that. Both were represented in the data sets that Ken showed. We tried using GPR and for concrete inspection, especially for detecting dowel bars or steel in slabs, and found a ground coupled antenna is more than suitable. Do you agree?
Yeah, I agree. You just get more detail. You do see, and I have data on dowel and tie bars with the air launched. It's to do an overall evaluation. You can use the air launched data, and our software actually detects it also using air launch data, but ground coupled gives you the higher resolution.
Excellent. And last question, I'm assuming from someone a little snarky in English. Does GPR keep you young? Peer-reviewed, sample size equals Ken.
Who wrote that? Oh, Paul. The answer is yes. Yeah, I have GPR every day for breakfast, and just makes my day.
Excellent. Well, thank you very much, Ken. That was an excellent presentation. And please, everybody, if you've got further questions, you can send them over to us, and we'll try and answer them for you. And again, we'll send this out, and look for the summary and the PDF of the presentation over on our website. Ken, thank you again. You guys can all find him at infrasense.com and various technical conferences around the year. And I appreciate everyone attending today. Thank you very much, everybody. And thank you, Ken.
Thank you. Thank you, Kent.
Bye, everybody. Bye.